We're going to do some experiments today that show the science associated with fire. My name's Morgan Hurley. I'm a fire protection engineer. Fire protection engineers use science and technology to protect people and property from fire. Don't try this at home. We have special equipment here in the lab that you don't have at home that'll make sure that the fire doesn't get out of control. I've filled a beaker with some water and dish detergent. What I'm going to add to this is some propane. Propane is a gas that's slightly heavier than air. You might use it in a barbecue that you have in your backyard. So what I have here now is a beaker filled with bubbles. And if I light it, tell me what's happening.
I think it was combustion.
It was combustion. What was burning?
The propane gas inside the bubbles.
The propane gas in the bubbles. What did the bubbles do?
I'm guessing the bubbles held the propane.
That's right. Propane is a gas made up of carbon atoms and hydrogen atoms. Who knows what the products of combustion are when you burn a molecule that has carbon, hydrogen, and oxygen?
Carbon dioxide and water?
Correct. Does anyone have a gas stove at home?
I do.
Why do you need a spark or a pilot to light a gas stove?
To give it the energy it needs to start.
Do you know what the term is for that amount of energy that it takes to get the gas stove to light?
Activation energy?
Activation energy, that's correct. What I have here is a standard Bunsen burner and a candle. If I turn on the gas to the Bunsen burner and strike a flint above it, it'll light right away. And then it keeps burning without the spark. Now, can I use the same spark to light the candle?
No,
Why is that?
because there's no gas for it to ignite.
Now, I can light the candle with a lighter, but notice that if I quickly put the flame there, it won't light. It takes a second or two for me to continue to have the flame on the wick for it to ignite. So what do you think is happening during that time that the flame is in contact with the wick?
The wax is melting and the melted wax vaporized.
Who knows what the three states of matter are?
Solid, liquid, and gas.
What state of matter is the wax?
Solid.
So if I blow out the candle and then quickly light it, it lights more quickly than the first time. What's the difference?
You had a liquid wax right under the wick.
Right, so why do you think it took less time when there was liquid wax to light the flame than when there was just the solid wax?
Because it took less energy to turn the solid wax to liquid wax.
Correct, because the liquid wax is already there. So one other thing we can do with the flame is if I blow it out, remember we got that white smoke before, I can relight the candle without even getting the match to touch the wick. What I've done is I've taken an ordinary coffee filter and I've cut it into a little circle. And I'm going to place it into a petri dish that's filled with heptane. Heptane is a hydrocarbon that's slightly lighter than gasoline. So if I put it in there and I ignite it, what's happening to the filter paper?
It's not burning.
Well, we talked earlier about the three states of matter. So what state of matter does fuel have to be in to ignite?
Gas.
What state of matter is the heptane in as it burns? Liquid. When we lit the Bunsen burner, what state of matter was the propane?
Gas.
And when we lit the candle, what states of matter did we see there?
Solid and liquid.
What state of matter does something have to be in to burn?
It has to be a gas.
If I light the Bunsen burner, this is the kind of flame that you're taught in chemistry class. If we close the air supply, the flame looks different. Does anybody know why the two flames look different?
The gas doesn't mix with air until just as it leaves the barrel.
That's right. Before, the gas and the air were mixed before they burned. Whereas when I close the air supply, the gas and the air don't mix until right when it's about to be burned. We call these two different types of flames pre-mixed and diffusion flames. In this case, the air and the fuel mix before they burn, and we call this a pre-mixed flame. If we close the air supply, the air and the fuel don't mix until right when the fuel is about to burn. We call that a diffusion flame. I'm going to take an ordinary wooden match and insert it into a paper clip. And then I'm going to take the paper clip and I'm going to place it into the barrel of the Bunsen burner. Now I'm going to turn on the gas again and I'm going to light the Bunsen burner. What's happening to the match?
You'd expect it to light or to burn.
That's right. So we're going to try and figure out what the shape of the flame is. What's happening to the match? It's burning. It's burning. Yep. So to explore the shape of the flame, we're going to relight the candle. Now with the Bunsen burner, we learned about pre-mixed and diffusion flames. Does anybody know what type of flame that is on the candle?
Diffusion flame? It's a diffusion flame because the oxygen in the air and the fuel from the candle mix at the flame.
So where is the wick with respect to the flame?
It's completely inside.
Because I'm trying to figure out what the shape of the flame is in 3 dimensions. When I first start to see smoke, I'm going to put the match into the smoke. It puts the match out. If I lower the mesh further into the flame, and the smoke changes color, I can put the match back and I can actually light.
Oh, that's cool.
That's so cool.
If I lower the mesh into the flame, so what do you notice about the flame now that we can look into it?
Well, it's a circle.
It's a circle, and is it homogeneous or not homogeneous?
It's not homogeneous.
That's right. So what do you think is in the middle of the flame where it's not burning?
Is it just gas?
What kind of gas?
Vapors from the candle wax?
That's right. So if I lower the mesh into the flame, I start to see some smoke. And the smoke that I see at first will put out the match. So what's happening is inside the flame there's just gaseous wax, and outside there's just air. And where they meet in the correct proportions for burning is where you have the flame itself. So what we've done with these experiments is to kind of learn some about what's going on in diffusion flames. We're interested in diffusion flames because the types of fires that you typically have in homes or businesses tend to be diffusion flames. In the lab, when you use a Bunsen burner, you generally want the pre-mixed flame. Fire spread is basically the ignition of things that aren't burning yet by things that are already burning. And to ignite the things that aren't burning, heat has to be transferred. And there's 3 modes of heat transfer.
There are conduction, convection, and radiation.
What's conduction?
Conduction is the transfer of heat through objects.
And what's convection?
The transfer of heat through air.
That's right. And what's radiation? The transfer of heat through electromagnetic waves. So what I've done is I've taken a piece of shortening and I've impaled it on a copper wire. Let's observe what happens to the shortening. So we'll ignite the Bunsen burner, heat up the copper wire. So let's see what happens. So what happened there?
The flame from the Bunsen burner came in contact with the copper wire. It melted the shortening, and the shortening fell off.
What I'm going to do is the same thing, but this time I've put the shortening on a glass rod. Place the Bunsen burner under the glass rod. Is it melting at the same pace, slower or faster than when we use the copper rod?
Slower,
Why do you think that is?
because the glass conducts heat worse than the metal.
That's correct. Glass is a poor conductor of heat, whereas copper is a good conductor of heat. So what's something that we commonly use to put out fires?
Water?
Water, that's right. Water is desirable from a fire suppression standpoint because it absorbs a lot of energy as it's heated, but sometimes water is not the best thing to use to put out a fire. Can anyone think of what one of those times might be?
A grease fire?
Grease fire is right. Grease is a non-polar solvent and water is polar, so that they won't mix. So I'm going to simulate a grease fire in this pan. What I've added is some heptane, which like grease is non-polar, and here's some water. So if I have my grease fire, and I pour, now you'll want to stand back for this. If I pour some water on, it won't go out. And that water would eventually boil, which would splatter and spread the fire. The best thing to do is just cover it. You can use things other than water to put out fire. Let me light this candle in this little beaker. I'm going to make some carbon dioxide by mixing some baking soda and some vinegar, and that'll give off carbon dioxide gas. The gas that it's releasing is carbon dioxide. Carbon dioxide's heavier than air, so it's sitting in the beaker, and I can pour the carbon dioxide out of the beaker, and it puts out the candle.
Whoa!